Welcome. You're about to listen to a presentation by Professor Ayşegül Gündoğan, Professor of Civil Engineering, Earthquake Studies, and Applied Mathematics at Middle East Technical University. The presentation of Ayşegül was part of the program of the fourth panel organized by Çare, as part of the panel series Turkey and Syria After the Earthquakes. Ayşegül received her PhD from Carnegie Mellon University in 2006 with her thesis focusing on full waveform inversion for seismic velocity structures. Dr. Askan's field of expertise includes engineering seismology, earthquake engineering, scientific computing and numerical methods, effects of simulated ground motions on structures, multi-scale seismic risk and loss estimations in urban regions, structural reliability and parameter estimation problems for site characterization. Dr. Askan holds several administrative positions in education and research. She is the department head of Earthquake Studies Program and vice director of Graduate School of Natural and Applied Sciences at METU. She is the current General Secretary of Earthquake Engineering Association of Turkey, a member of the National Disaster and Emergency Consultancy Board of Turkey, and a board member Cosmos and European Seismological Commission. Dr. Askan has led and participated in several EU projects, Turkish-Japanese bilateral projects, and national projects focusing on seismic hazard and risk problems.
So hello everyone. Today I would like to talk about how extreme the recorded ground motions of the February earthquakes were, and I would like to relate these seismic hazard levels to the recorded ground motions and damages. The tectonic setting of the area is the East Anatolian Fault Zone on the very east of Turkey, right here, and we have always hearing about the North Anatolian Fault Zone. That was until 2020, the Samos Island earthquake in the west of Turkey in the Aegean Sea. But East Anatolian Fault Zone has been as active as the other fault zones in Turkey, and it has some interesting features which reminded itself, unfortunately, as of February this year. Well, Turkey is tectonically being pushed to north by the African and Arabian plates, and we're on the Anatolian block. We are actually rotating towards the west, and as a result of this huge tectonic motions, we have very, very large earthquakes in this country. One of the largest occurred on February 6th. So this figure is by our late Professor Aykut Barka in 2002. It shows the historical events on the East Anatolian Fault Zone. He was one of the people who understood the importance of studying this particular region. And he indicates that the last event around Kahramanmaraş was in 1114 and also 1513. So that's really a huge time ago. There was another one in the 18th, but these are far south, closer to Antakya, which is well known. After this figure was drawn, we actually had the 2010 and 2020 Elazığ earthquakes, and the only gap on this fault zone was these regions, which showed the USGS fault plane positions in two colors. So nature actually fills the gaps one by one in time, except we never know when the next action is going to be. And these two events were really very particular scientifically as well, because they followed each other. About 9 hours later, the first event, we had another MW 7.5 earthquake, and this is very rare in nature. So this was very particular for this region. And to my surprise, when I was working on the ground motions of the first earthquake, which is shown here in the red colors, this is the first event, fault rupture, which is about 400 kilometers, which is really very long. When I was working on the ground motions of this event, of course, we were sleepless all night. I realized that I'm moving in the east-west direction, And I told my students there's another earthquake. Probably it's closer, and probably it's either very large and it's in the east-west direction. So I could feel the motions of the second one, the one in the blue, in this figure on the left, the second earthquake, 7.5. And imagine how far I am in Ankara from actually Addistan. So this should tell us that, and I could tell that we were moving in the lateral direction, in the east-west direction. So these ground motions were really large, and their effects were observed in multiple cities in Turkey, including Ankara. So our previous studies in the region, researchers always talk about the fact that, oh, I have said this, I have warned people, but let's look at what we have published in the past. And I never talked about this on media. I never accepted any media talks, but I would like to talk about it right here, right now. After the 2010 Elazığ earthquakes, we had published with some co-authors from MITU, Asia, and actually USGS at that time, we had said that the stress may induce other earthquakes moving to the south. So we can have other events. And really what happened is the 2020 event and then followed by the recent ones. Another study we had performed is I practically spent my life, my last 16 years since I came back to Turkey, on doing scenario earthquake models. And it's not easy to publish these papers in international journals because these events didn't happen yet. You can publish tons of papers about the Kahramanmaraş earthquakes right now because there's data, you can validate it, you can discuss the features, which is very important. But before an event happens, it's really not easy to convince the practical and the scientific world that this region is important. And in actually year 2022, 1 year ago, we had published this paper about the Gaziantep region. This is not the same earthquake, but we have underlined the fact that the high seismic hazard, coupled with the vulnerability of the structures in this area, we could really see a destruction here. This is the let's say the damage ratio map of Gaziantep region. Please note that this particular scenario did not occur, as the design earthquake of Gaziantep didn't occur yet, which is also should be underlined. But the darker areas that show high risk are the areas where a smaller number of buildings were either damaged or demolished in this earthquake. So actually we had kind of a validation. And to your surprise, this is actually something really makes me very sad. We had an AFAD-funded national project. AFAD really funded MITU and a couple of other universities, including Kahramanmaraş University. We were actually performing a project which was entitled Development of a Method for Urban Resilience Evaluation, and it was a Türkoğlu Kahramanmaraş case study. And please note that this figure on the right, on the top, was drawn 1 year and 3 months before the earthquake. This was the spring of, actually fall of 2021 or the new year of 2022. We had foreseen, we could guess that it was possible to have 3 different scenarios near Kahramanmaraş. We could see that there could be a 7.46, 7.5, 7.3, and a 6.7 in south of Kahramanmaraş. But what really happened is this entire fault ruptured and we had a much larger earthquake. And this project was still going on. And before its completion, actually 3 months before it ended, we had this February earthquakes. And when my fellow professors tell me, oh, you could see that, why did you not publish before the earthquake? And I always answer them, it will be very difficult to really persuade people, to tell people that this region is really risky. So this we will come back in conclusions, but we have to underline the importance of scenario events, and we have to believe them that one day they can happen. So was the 7.8 event anticipated? Well, of course it was anticipated. We are not probably the only ones who were saying that this East Anatolian fault zone is risky, but the total rupture of the real event corresponds to 5 different segments in the Turkish active fault map. And this fault map is actually renewed about 5 years ago. And the authors, they state that multi-segment ruptures are very common on the East Anatolian fault zone. However, no previous studies modeled such a large rupture that will consist of 400 kilometers. And here is the spatial distribution of peak ground motion parameters of the first earthquake, of the Pazarcık earthquake. We see that on the left, the peak ground accelerations are pretty high along the fault surface. They're reaching about 0.75, 0.9 sometimes over 1G in Antakya. And we see that the peak ground velocities are actually even higher than anticipated. They reach levels of 150 centimeters per second. In 1 second, the ground is moving 1.5 meters. That's really huge number for these earthquakes. And let's look at the spectral accelerations. Spectral accelerations determine the behavior of structures of that particular period. And on the left is the response of the short period structures. Basically, we see that the numbers are reaching about 1.5 G. And on the right, we have the long period spectral accelerations. It's more incoherent, but again, close to the Antakya Basin in the south, we have really high values because of the basin effects I will mention. How about the modified Mercalli intensities? Modified Mercalli intensity ranges from 1 to 12, and 12 is total destruction. Starting from 4, you can feel it. 1 to 3 is basically for computation purposes. And this was the first time I ever computed MMI 10 and 11 from a real earthquake, from a real event. From the accelerations, we could go to the intensities. And this is remarkable because this is important for the first recoveries and the short-term disaster response. And these values are really, really incredible. The recorded motions I will share with you today are summarized in the METU report in chapter 4, and I am providing the links right here. I would like to show you one motion in Pazarcık, Kahramanmaraş, right here. It's actually at the conjunction of the two segments. What you see here is the ground accelerations in 3 directions, 2 horizontal and 1 vertical, up and down, the Fourier amplitude spectra for the frequency content, and the spectral accelerations. While the spectral accelerations show broadband response, which means a very wide type of structures are affected, and the time series have multiple wave packets. When you talk to the citizens in the region, they tell you, oh, professor, we had 3 earthquakes, we had 4 earthquakes. No, there was 1 Pazarcık earthquake, but the fault is so long that they felt like it came, they had the big shaking, and then it stopped, and it starts once again. The rupture is too long, and it takes actually a lot of time to recover from such an event. When they could stand up again, could go to the doors, they were being shaken once again. So this multiple wave packets is one of the reasons why so many structures were being actually really severely damaged. This is in Kırıkhan. I'm showing you another time history in Hatay Kırıkhan. It's a very broadband response spectrum. Normally, a response spectrum would have peaks in the short period, intermediate period, or the long period range. But this is very broadband, which means taller structures are actually having a lot of excitation here, and the shorter structures are also being shaken really hard here. What is interesting is the ground motions are beyond the Turkish earthquake design spectra for 475 years, and they are touching the 2,475 year spectrum once again. So we will come back to that in a couple of minutes, but I would like to play a video first to tell you what's happening. The first pulse comes, and then you have a short period response, and then when the second or third package comes, you have actually a very broadband response spectrum. Normally, engineers would do this statically, but I made a video with my student to show you the extent, which means everything in that period range, practically all human-made structures, are being shaken very severely. So one damage picture from the field, that is the station 1415. Actually, you could see that there was a water tank here. I took the picture on the right in March, and this was uploaded on the Google Maps photos 2 days prior to the earthquake. I still don't think that building the water tanks such slenderly is a good idea, of course, for pumping purposes, but look at what happened. This shows the fact that the long periods are excited very clearly. There's a long period effect of this earthquake. Let's look at the strong ground motion data against our anticipations. The curves are empirical equations from the past earthquakes. And the data are shown here with the dots for different site classes, for softer soils versus for rocks. And what we see here is peak ground accelerations confirm the anticipated motions, but the peak ground velocities are much higher than what's anticipated. Then someone can ask me, but you never had such a big event in the past, so your equations are clearly not correct, which is also true, but we always check the previous earthquakes data with the current data. But peak ground velocity is something that's really huge in this earthquake. Now, how extreme were these events? This is the NGA West 2 database that has the entire world's ground motion records. And look at 3 Hatay records here. We plotted the maximum ground motion levels that were recorded before all over the world: China, Taiwan, Japan, Canada, New Zealand. And now look at the records from Hatay. We are exceeding them at some periods, and we are very close to the maximum ground motion. So the event was clearly a disastrous natural event. Now, the photos from the field, I will keep this part very short because you have seen a lot of figures before, and I want to talk about the philosophy more than the pictures. This is a textbook picture. This is near Turkoğlu, my project center actually in Kahramanmaraş, where it's at the intersection of two segments, and the road is just offset by 4.5 meters. It's between 4 and 4.5 at different locations. And this is a left lateral motion. When you look at the sideways, you see that your opposite direction has actually moved to the left. So this is a clear picture of the ground motion. And you have seen this photo before, I know, from Gölbaşı, Adıyaman, where unfortunately we don't have a lot of records, but the ground failure is actually very, very obvious. And people, when they look at it, they say, oh, people could survive. This is better than demolishing, but that's not true. You know, you're shaking with such a large acceleration, with such a large overturning moment that people were injured and they actually lost lives. And these are some ground failures due to liquefaction, all of them. They actually indicate that the soil is liquefied. It's not solid anymore. And it means you can't build your structures on such susceptible soils. This is a fault deformation, basically. And my colleague is sitting right here. This is the fault deformation itself. It passes through a 2-story building. This is another fault deformation near Nurda, which was severely damaged again. And let's look at the ground motions. There is no design earthquake ground motion level here because we don't know the seismic velocity structure there. But you could see that the ground motions are coming in wave packets again, and the response spectra is still very broadband. How about the structural damage in conjunction with the ground motions in relation to the ground motions? Well, we have very widespread damage in 11 cities. We see that the old structures get more damage, but it doesn't mean that the new structures, they all performed very well. This is something that should be investigated very clearly. More than 25% of the buildings are in moderate damage or in a worse damage state, severe collapse, heavy damage, and about 3,000 buildings are actually immediately lost due to the high damage levels. Well, the damage types are alike the previous failures we have seen in Turkey, but the area is huge. It's really, when you first go there after the event, it was so unreal. Like Inanç said it very clearly, and the area is vast. You cannot see the end of damage. We still had the soft story, weak story problems in the buildings. We had detailing problems with reinforced concrete structures. Reinforced concrete is very popular in Turkey, in all maybe developing world, but if it's not detailed properly, it becomes a grave. It becomes a horrible grave. It's a very heavy material, and you have to do the detailing really well. If you can detail it, it's fantastic. If you can't detail it, it's a grave. So there is low concrete strength, as always in Eastern Turkey, and there is still undripped plain reinforcement bars that is not allowed in the Turkish earthquake code right now. You could read more in chapter 5 of the METU report. And I will just show you a couple of pictures here. This is Pazarcık Kahramanmaraş. The reason I'm showing you this figure is there's some structures that are intact. They're really intact. You can see some fine cracks, but people just walked out of them. Versus a pancake type failure. And that's like one after another. Something in a light damage mode and another one in heavy damage. Another one completely collapsed, another one intact. So this always tells me that local detailing is very important because the ground motion levels cannot change from this building on the left to the next building. It's just not possible physically. And look at the mosque here. The minarets have just fallen down. This is long period enhancement of the ground motions. And this is another picture in Türkoğlu, in my project area. Of course, this is after search and rescue operations. It's really beyond the original demolishing, but they completely lost the building during the earthquake. And this is just 500 meters away. Again, people just walked out of it. It's not usable. They lost their homes, but they survived. They performed according to the life safety performance level. They prevented collapse in these buildings. And then you just move about another 500 meters to a kilometer in Türkoğlu, and you see buildings that are actually not demolished at all. So it is possible to build according to the standards, and it's possible to design according to them and to apply the building enforcement actually. Now, this is the ground motions that are measured in Türkoğlu in our project area. Please note that we are again above the design level earthquake here, but some of the structures did not just fail. So it's not really only about the mathematics, it's about the behavior of the structures. Well, this is Antakya, our beloved Antioch, and it's such a peaceful city. If you haven't seen it before, it's such a loss, but Antakya keeps coming back every 200 years, and hopefully it's going to be going back to its beautiful days very soon. I have taken some ground motion stations and some pictures here. Again, completely demolished, something that is standing still and people survive. Now, I had to call my friend to understand this picture. That was in March. And then what we could figure out with Alter Arabic from METU is two structures actually pounded each other, and then one of them then collapsed. So this shows the importance of the pounding effect. So one structure has its very weak components like windows, non-structural components, and the other one has the huge reinforced concrete slab. When they hit each other, the weaker one is completely lost. So this is important. And another very, very well-known staircase issue, it's difficult for people to actually get out of these buildings during the earthquakes because stairways are the weakest parts, and when they get damaged, there is a huge problem. This is another textbook figure with the shear cracks that you could see. Look at the ground motions. Now, the ground motions are, again, beyond the design level earthquake. They are closer to the maximum credible earthquake, but then some multi-degree of freedom buildings do survive. And the reason is, this is the lollipop model of the buildings, but the real buildings are more complex. The fact that the ground motions are beyond the expected amplitudes doesn't mean that you have to collapse, that you have to lose lives, because the complex behavior of the buildings should have load redistribution. You should be able to transfer loads, and you should be able to let people get out of the building despite some damages, because in such big earthquakes, we allow damage, but we wanted to prevent life losses. We wanted to prevent the collapse completely. Now, this is Hatay, and the reason I'm showing you now, this time we're looking at the hill to the east, actually. This is our student Frat who's taking a picture. There is really nothing on the left, but on the right, you have pancake structures. So when people tell me, oh, it's the wave field in Hatay, of course, the wave field is incredible in Hatay. We have never seen such big waves ever in Turkey in the century. Maybe in 1939 Erzincan earthquake, but never again. But then if this thing can stand here, why don't we have these buildings also not collapse? That's my question. And there's a historical structure here that's much older than the others. When the newer ones have collapsed, with lower number of stories. There's an older one that's standing still, and this is the old, beautiful old town of Antioch again. These are the ground motions where you have broadband responses, where you are above the design spectrum, and you have to be very careful about the construction practices. Now, implications for future, my last 3 slides. Our Turkish seismic hazard map is pretty new. It's updated in 2018. It's a probabilistic seismic hazard based map. But I think we have something to even add to it, because people are claiming the design earthquake levels are not high enough or not. We could put more multi-segment ruptures in East Anatolian fault zone on the very east, actually. We can think about the sources and scenarios. It's possible to even further develop it in the future, but this was actually a conservative map as a probabilistic application. And this is the design spectrum. We have to think about how we will enhance the long periods in basins, basin effects, near field ground motions in the very near field area, near fault area. We have to think about site amplifications once again and liquefaction. And the ASD design spectra has now multiple period definitions. Maybe we will work on switching to that. But I should again remind you, Turkish earthquake code is pretty much conservative technically. Now, my summary, we had 2 consecutive events with very long ruptures, high ground motions. There were very high peak ground velocities overall. There were huge directivity pulses in Hatay, in Antakya, and we had a long period content and a broadband response spectrum. Well, civil engineering is probably the only engineering field where you cannot make a full test of your structure before nature hits that. So we had 2 consecutive force vibration tests on the structure in that region, on all structures in that region, and most of them actually passed that test, but 30% really failed incredibly, really, really bad. So we have to examine the event in detail and understand the structural responses, why these widespread damages occurred. Now, there's a memory effect that I would like to mention. After the Elazığ 2010 earthquake, when we were driving to Elazığ, flying to Elazığ 2020 earthquake, we were fearing that we would see a horrible scene. But we lost lives, of course, unfortunately. But 2020 was not as bad as it was anticipated, because people remembered. It was only 10 years ago that they saw how bad it was in 2010. So this memory effect is very important, because my project partners, some people who gave me food and drinks on the field in Kahramanmaraş, they told me later, oh, Professor, we didn't know it was so serious here. So people are not aware. They have to be aware, because they haven't had such an event in the last 16 generations. Anyway, so fault map, hazard map code are recently updated. What further updates are necessary? I'm in the code committee. We're still talking about it. How are we going to do relocations in Turkey in this area? Are the questions that I'm asking myself. And my final 3 points, we have to bridge science and local decision making. Otherwise, we will sit on our tables, write papers that nobody puts them into life, into real life, and nobody really does anything practical. Academicians should be more, they should take initiatives about this. We have to be more active, talking to the municipalities, maybe making them understand. And we have to have code enforcement and construction supervision. Please note that our global constructions by Turkish firms are pretty successful. So when there is code enforcement, we can do these things very well. Why not in Turkey? And we have to do scenario models in other regions in Turkey as soon as possible. We are working on many other places for years now, Bursa, Çanakkale, and other places. One by one, again, Erzincan, we have to make scenario earthquakes and study their effects before real earthquakes occur in this earthquake-prone regions. So these are my contact and the reports that we have been working on since February.